Okay, in this video we're going to talk a little bit about a linear programming example, and I'm going to show it to you two ways to try to explain what's going on. So what the problem would state is that I'm trying to maximize the objective function, which is p equals 2x plus y, and I'm going to say at a given point, and you'll see why, subject to the following constraints. So I have x plus 2y is less than or equal to 5, so I'm just going to click that, and it plots it for me. X minus y is less than or equal to 2. So if I click that, so you can see the feasible region kind of coming into view here. I need x to be greater than or equal to 0, and I need y to be greater than or equal to 0. Okay, so in amongst all of this, what I want is the region that's been shaded 4 times. So it's this region right here, which turns out to be a pentagon. So what I'm going to do is I'm going to turn off some of the shading. So I'm going to just graph the lines, and I'm also going to create a polygon out of it and turn off these inequalities, so I don't want to see them anymore. Okay, so this is my feasible region, and what I'm going to do is I'm going to locate the corners of it. So I need to solve a bunch of systems, which I would do by hand if I wasn't using the computer, but I'm using the computer, so what I'm going to do here, I've already done it, so if I show the objects, I get a point here at 0, 2.5, at 3, 1, at 2, 0, and at 0, 0. So those are the corners. And what I've also done is I put a point, and this point is inside the feasible region. And what I'm going to try to show you is what happens. So if you've done these problems before, you know that the solution that we're looking for, the maximum, is going to occur at one of the corners. So what I'll do is I'm going to... So right now the point is at the point is located at 1, 1. So I'm taking x is 1, y is 1. I'm plugging it into the objective function, and it's evaluating it. So at 1, 1, the objective function gives you 3. I can move it around. You can see that we're getting smaller, so that's not what I want. If I move this way, it is getting bigger. If I move along the x-axis, you can see that it starts at 0, and I'm trying to get on the x-axis. It's getting larger as I move. If I move in this direction, it gets bigger. And in fact, the place where it's the largest is going to be right here. So I'm going to get 7 as my maximum. But I can move anywhere inside the feasible region. I just don't get the largest values. So what I'm going to try to do is show you why that happens. And I'm going to need to use 3 dimensions to do that. So what I'm going to do is switch over. So this is GeoGebra that I've been using. I'm going to use Grapher now. So Grapher is a program that comes with a Mac. If you search it on Spotlight, you should find it. I'm going to do a lot of math, or I've done it in the background. I've done a lot of math that you don't need to understand to see what's going on. So this, when you're looking at 3 dimensions, the x-axis is over here right now, the y-axis is over here, and then the z-axis goes up and down. So what I'll do is I'm going to reproduce the feasible region using 3 dimensions. So there it is. So hopefully you kind of recognize it. If I move this, see, it kind of looks the same. So there's my feasible region, and what I'm going to do is I'm actually going to, in 3 dimensions now, I'm going to graph the objective function. So the objective function was p equals 2x plus y. So I've changed it to z equals 2x plus y so that I can graph it. And you see there, it's actually a plane. So it's flat, but it's tilted. So that's the reason that the maximum is going to occur at one of these corners. So let's look at what happens. So you have to understand a little bit about 3 dimensions. In 3 dimensions, the equation of the x-axis, no matter where you are, is y equals 0. In 3 dimensions, y equals 0 is actually a plane that goes up like that. So what I'm looking for is I'm looking for the intersection of the plane y equals 0 with the plane that is our objective function, and I want to limit it so that it's only on this feasible region. So what I've done is I calculated that before, and I get this. Okay, so you can see that intersection. It's going to be a line, and what I'll do now is I'll turn off the plane that is the x-axis and just leave that. So along the x-axis, you can see that the value, so the z value, the height you get, increases as long as you move along the x-axis, which is why when I was using GeoGebra, as I moved along the x-axis, you can see that the objective function just keeps increasing. And that's because of the way that that plane is tilted in 3 dimensions. So we have that, and then we just can kind of repeat the process. So along the y-axis, which if I turn off the objective function, the y-axis is right here. So along that, what I'm going to do is plot the plane that is the y-axis. So the y-axis is x equals 0, so that's going to give me this plane. And what I want to do is I want to find its intersection with the objective function. So this is all the math that you don't really need to do, but I'm looking for this line right here, and I already found that ahead of time. That looks like that. So if I turn off this plane, you get kind of a better picture. So we see that, and you can tell now at this point that if you moved along the x-axis, you get a bigger value out of the objective function than moving along the y-axis. But still, at this point, the biggest values we get are at the corners, right? As far as we could go on the x-axis was 1 corner, and that's the highest it is. As far as we could go along the y-axis was another corner, and I can move up. And then I repeated the process, so doing a little math that you don't need to understand, really. I repeated the process. I graphed this plane and found the intersection. So it's up there. And then I graphed the remaining part and its intersection. And it looks like this. So the easiest way maybe to understand this is that the lines that you're graphing in 2 dimensions, let me stop this spinning, it's slowing me down. The lines that you're graphing in 2 dimensions, when you graph them in 3 dimensions, are planes, and they're actually vertical planes. So they're kind of like the walls of a room. And the objective function is also a plane, and what it is it's kind of the roof of that room. So what you're looking for is you're looking for the highest point on the roof, and if you just think about it, as long as you have a you have perfectly straight walls and you have a perfectly flat roof, the biggest value and the smallest value, the biggest height of the roof and the smallest height of the roof, must occur at one of the corners, and that's why it works the way it works. So I hope this helps you kind of understand that, because I know that usually you're just told because it works, and I'm kind of also just telling you because it works, but I'm trying to show you at least a little bit how it works. So think about a room with a roof, and you're looking for the highest point on the roof or maybe the lowest point on the roof. That's got to occur at one of the corners of the room. And I hope you found this helpful. Good luck.